All right, hi, and welcome to our next lesson here in School of Management 609. And today we're going to look at logit classification in scikit-learn. Now, if you recall from your stats class, I'm not really going to cover everything, every kind of test and everything you should do with your logit analysis. But realize if there's something that you think you need to apply to the data that you learned from stats class, there probably is a routine in scikit-learn. But this lesson is more on how to do that stuff in Python. So we've got a data set again from Kaggle. The data set has information on patients and whether or not they showed up for their doctor's appointment. Patients that don't show up for a doctor's appointment are expensive because the doctor's got a certain amount of time they can't bill for. So that's why they like to do it. Remember, this is a teaching data set from Kaggle. So we're going to use the data in it and do what the data says, but don't think of this as the data in here is accurate for any particular doctor's office. It may not be. Okay, so let's go. We're gonna read the data set. We're gonna drop the non-numeric column. So we'll first do a logit classifier based on just the numeric columns. We'll see how that does. And then we will bring in we'll look at a transform for a skewed column, and we will look at what happens if we bring in a categorical column. And so again, I'm going to bring in the categorical columns individually. You could obviously go further and make combinations of features and do some feature engineering, which I'm not doing here. I'm mainly just looking at how do you manipulate the data frame and do different types of analysis in scikit-learn. But if you looked at the table of contents in scikit-learn, there's really a lot more in there. So let's get on with it. Read the data set from Kaggle. Basically my imports, I just built this list of imports as I used different methods throughout this. So this list of imports covers all the libraries that I use in this notebook. Don't think you would build this, you wouldn't build that ahead of time. Like, so if you're writing your own, as you use a new library, you go, oh, okay, well, I'll add that to my import list. So I didn't know this really going in until I went through the analysis that I wanted to go through. This next code, I set the file name of the data set, and then I put it into a variable called orig underscore data frame, right? So you've seen a lot of published things about scikit-learn. The main data frame is usually just called df a lot of times. I use original data frame so that as I manipulate the data frame, take columns in and out, I can refer to the original if I want to. So that was my justification for calling this original underscore df, because if I make changes, I'll have something to go back to. And then I usually just print something out here to show that we got it, right? So we've got the head method prints the first 5 rows, and the shape method prints out the shape. And so we can see there are 10,000 observations in this data frame with 30 columns of information. And so, but that printout was really, you just want to begin to understand your data set. Make sure you did, in fact, receive a data set that you think you received. And you can see we've got, some of the column names here, patient ID. So I know I have the data set that I was interested in. Now, just as a simplification, and so I can jump right into logit analysis, I'm going to drop the non-numeric columns, right? So if it's the numeric columns, we can use in logit analysis directly. Non-numeric columns are categories, and so we have to change those into categories. So I'm going to do a little bit of that later, but right now I'm just going to drop the non-numeric ones, and that is done. Let's see. Oh, well, first I do check for missing values here, right? So there is no, these zeros here indicate there are no missing values. I did that with original df dot is null sum. So I summed for each column. And that's how I got these zeros. And then here I select the columns where the data type is object, and or excluding where the data type is object, and I put that into a variable called numDF. So I keep my original DF is what I read in from Kaggle, and numDF is the original data of all columns that are not type object. And so I've printed out. So these, to print out the data types of your columns, you can do your data frame dot D types. I printed that out before and after dropping the object column so that I know what happened. So that's kind of like a general technique. A lot of these, some of these lines of code, they're a little bit cryptic, right? And so you're a little unsure, do I have what I think I want to have? So here what I did is I printed out all the columns and their data types. And you can see I have integers, objects, and float. Objects are generally speaking or strings, although that's changing. Pandas is changing the way it handles strings. But in this example, everywhere it says object are really strings, and those strings in this example represent classes. So anyway, so here's my data types. I drop everything that's of data type object. I reprint the columns with the classes, and I see I only have integers and floats left over. So print, drop the classes, print again, and see what changes. Again, a general technique, if you're doing any kind of transformation of something, you might want to check the shape. Did the shape of your data frame come out the way you thought it should? All right. And then, so just in exploring the data here, I'm going to check out, here's a heat map correlation matrix printout example, right? So I get the correlations here, and then I plot them in this with this heat map. And this 14 by 10, that's the area that I've reserved for it. This format equals 0.2f is where I change the decimal places to 2 decimals. If you'll have to fool with those arguments to get something readable on your screen, right? Depending on the size of your screen, the number of columns and stuff like that. So sometimes when you take the defaults for these printouts, they are unreadable and you have to adjust those. So I just took all numeric variables, I made a correlation heat map, and I wrote the correlations to 2 decimal points. And again, this is what I would do early in my analysis because I basically don't know what the data looks like. So I'm just putting this out there to check things. It's a good way to start checking things out. And so most of it is very low correlation. My target variable, no-show. Remember I said we're trying to predict no-shows? So the no-show is the target variable. So this no-show row is, of course, important. The correlations are not strong, which means we've got a challenge ahead of us. But one thing you'll notice, these strong correlations are not useful to us. So we're trying to predict if somebody's a no-show, and these are actually the cost to the organization if the person does not, or when the person does not show. So these are things that come after they don't show, then they cost the organization. So they're not predictive variables. We don't have that data until after they don't show, then there's a cost associated with that, and that's added to their record. So that's why they're super highly correlated, right? The 0.94 is just because when somebody doesn't show, then they incur a cost, and these are two different kinds of costs. And rebooking is, well, if they showed up, they don't have to rebook at all. So that is also a consequence of not showing up. So these three variables are not used, don't make sense for our analysis of predicting the no-show. There other analyses could be done with this data set. So these three variables I can't use. Then look at these white lines. The white lines means correlations could not be calculated. And that's because these features, patient previous no-show count, are the same value for every observation, and therefore a correlation, they have no variance, and a correlation can't be calculated. So these two, so I'm pretty sure what's going on in this data set, right? Patient previous no-show count, it's just zero for every patient. And so we don't really have good data on that. So again, those two features, not useful to analysis. So from this, I've definitely eliminated some features. And again, to figure this out, you can look at this heat map. It helps you, gives you some clues, points, it gives you some red flags. But you really have to go back to the data set and understand what does that feature mean. So, in real life, you'll know where the data came from. You'll be asking people, where did you get that data? It looks funny, things like that. So in this example, let's keep going. I've also printed out the variance of each column, which also shows a zero variance on those two columns that we're showing as they show as blank white space in the previous heat map. So this is just variance of columns you can print out. And then so we have now determined that all of these columns, so the patient no-show rate, slot booked flag, revenue lost, also the IDs, right? A patient ID and an appointment ID are not good for predictive analysis either. So these are the columns or the features which I determined both from reading the information on Kaggle about how the data is set up and a little bit of hints from the heat map. And so they all need to be dropped. So I'm dropping all those columns here. So now my num-df here is the previous numeric df with the columns dropped off here. And I just reprint my correlation matrix. And now I don't have the weird things are gone. Although I do observe that I've got very low correlations. Again, my data is actually not going to be that predictive, but that's okay. So now let's try a logit classifier on those numeric features, right? So num-df is my data frame, and I've dropped non-numeric columns, and I've dropped numeric columns that don't make sense for prediction, right? And so now that I have that, I can make my x and y, right? The y is the target variable, no-show, and the x is all of the features except no-show. And so that's how I'll make my x and y arrays. And then I'll use train test split. Train test split is a part of pandas, and train test split allows me to divide the data set into training data and test data. And that'll mean I'm training on one group of data, and I've set aside another group to test on, which makes my test more accurate, right? I'm training on one set, testing on another. I'm not training on the whole data set and relying on the accuracy in the whole data set. So this train test split, very important. It takes your x and y, takes a percentage. I took 20%, put it in my test scenario. Random 42, that means the train test split will come out the same every time. And so you don't really need that, but it gives you consistent results if you want to demonstrate your results. And so model, right? Model is an instance of the logistic regression class, right? So just getting back to model is going to be an object, right? Just kind of like hotel was when we did our own model. And the class is logistic regression. And I've given it an iteration. You'll notice I've commented out the one without an iteration. So um, the logistic regression model, when it trains, it iterates a certain number of times to find the answer, and then it stops. And I noticed that so that the more features you have, the more it usually has to iterate. Um, and so I found that when I use the default value, it quit before it found an answer. But it will give you that error message, so it's not really a big deal. So now we train it, and we've got an ROC that the how much we've improved our um, probability over just guessing. So at 0.61 is actually pretty bad. But that just goes to the quality of the data in this data set. It's not remarkable because 0.5 is what you would get if you guessed, and 0.61 is what we get when we use the numeric variables. So in fact, our data is not a really good predictor. We're only getting 20% better than guessing. However, that may save us money, right? So a little better than guessing sometimes saves a significant amount of money. So there's some help. But that's what I've done here. I've made a model. I've fit the model using the training data. I calculate the probabilities of all my predicted values in the test set. Right. So if you recall, logistic regression, we use it to classify, is this person going to show up or not show up? We can put them in those two categories, but it also gives us a probability, right? So you could say, what's the probability someone will show up? So for every predicted test case, we actually get a probability, and I printed out the first 5 here, right? So the first patient has a probability of 0.19 of showing up, okay? Or actually, it's 0.19 of being a no-show. So 20% chance this person won't show up, 22% chance that person won't show up. So it's a classifier, but we have also have a probability, so we could rank order our observations or something like that if we wanted to do that. It's not really a true probability, but it's something we can use more to rank order those incoming tests. So space, that's the area under the curve of our improved decision making. Now, so that's my logistics model based on numeric values. I want to do a couple things. Here, I just want to show you this. Say I wanted to do something for every column in a data frame. I can use this for loop. So this for loop just loops through every column. So for column name in numdf.column. So numdf.columns, it gives us back a list of columns in the data frame, and therefore we could do something with each column. And I point this out because you might want to say, how good is important is each column at predicting things. In this case, just to show you the for loop of columns, I printed out the column name. So for column name, print df, and I get print out my list of columns. So that just wanted to show you that. And then check how each column of the df would work as a predictor, right? So we can make a logit model based on just one feature as a predictor and print out its ROC, and right. And so like some of them actually hurt us. The no-show itself, I just left in there, didn't delete it. So it shows a 1 there, but as a perfect predictor, obviously. But so you can see the strength of different columns, and none are particularly strong. Age is a little bit better than some, gives us a little bit more information. And appointment hour seems to give us a negative impact. All right. So that's, does any one column, one feature alone work well for your analysis? My point here is just to show the for loop and recalculate the ROC for every individual numeric feature. So let's move on to with skewed data. Now, so these variables, my features, are heavily skewed, right? So to measure the skewness, we do the for loop, we go through each column and measure how skewed it is. Values substantially above zero here show our right skewedness. So our patient total appointments is 1.68 is our most skewed variable. So I'm just going to do a um, logarithmic transformation on patient total appointments to see if that makes an improvement. So you could consider a transformation on any of these variables because they are all, reminder hours is not that skewed, but many of these are showing fairly skewed. And so you would consider doing a transformation on the skewed data to make it work a little better. In this example, it makes a small difference. So here I take my numeric data frame and I add a new column called patient total appointments log. So that's a new feature being added. And I'm saying that is equal to, and this gives me the log transform. So this is built into NumPy. So give me the log transform of patient total appointments. And I add that feature. And then I drop the plain old patient total appointments, right? I'm not going to use that feature. And so added a new feature, drop the old one, and then I make my XY based on those and redo my analysis. Let's see. I kind of wanted to point out some weird syntax, right? When you see a dot, see we have NP dot, that actually can have two different meanings. Right. So when we saw, right. So here, right. See the dot? The dot numDF is a data frame. Column name means we're just looking, column name means to substitute the variable column name here into here. So select a single column of a data frame. The data type of a single column of a data frame is also a data frame, so that remains a data frame. So dot skew means calculate the skewness of that column of the data frame. So the dot means a method that can be applied to data frames, right? And that's the same. We did that with hotel and things like that in the past. This dot is slightly different, right? So we imported NumPy as NP. This NP is not a variable. This NP is the NumPy library. So log LP is a function in the NP library. So see, the dot is sort of playing a slightly different role. The thing after the dot could be a function in a library like this, or it could be a method for that object. And that's why you'll see the argument to the function is our numDF, right? So up here, numDF is itself an object and has a method in it. Here we're calling a function and passing it numDF. So it's kind of that dot has a slightly different meaning, and it's what makes the syntax of Python look a little confusing because the same thing means something a little bit different. So you'll have to realize a library can have a dot after it, or an object can have a dot after it. So that's that. And so I substituted I took the log of the patient total appointments. I redid my logit analysis, recalculated my ROC, and it did in fact go up a tiny bit, but not much. So with the transform, my logit analysis is up a tiny bit. Really made very little difference. It worked about the same with or without that transform. But there are times when that'll make a bigger difference to you. Then now, so far we did the numerical. We used all the numerical variables. I transformed one of those numerical variables in this example. Now, and again, I could do more, but I'm going to just taking all the numerical variables and adding in one categorical feature and checking if that categorical feature improves our ROC. So what I did, again, I've got my for loop on column name, right? And it's on, but we're looping through object columns. Object columns are the original data frame. That's why I named that original. I use the original DF and the numDF. And I select all the column names where the data type is object. So object columns is a list of column names where the column was of type object. And so for every one of those column names, I'm going to do a transformation of the categories found in that column and add that transformation onto as new columns onto my numeric columns, and then recalculate my logit model based on the combination of all numeric features and one categorical feature. Now, obviously, we can go on, we can try some combination stuff, but that's just kind of how far I'm going here. But look how I do it. So for every column name and object columns, that means I'm going to execute this loop for every column that's an object in my original class. Okay. And the way I do that is I print out the column name so I can see what I'm working on. And then I make a new data frame. See this? This is an important line here, line 5, cat df. So that's a categorical data frame. And what it does is takes every value that shows up in that column and turns it into a binary variable, right? So if you have gender, male, female, or something, if there's two values in that column, you'll get two new columns, gender male and gender female, and each of those will have a 0 or a 1 in them. And then because that is actually redundant, because we will drop one of them. And so, and it could be other things like day of week. So day of week is Sunday through Saturday. There's 7 days of the week. We'll make day of week Saturday, and it'll be a 0, 1 if it's a Saturday. But because with all of them there, one column is actually becomes redundant, because if it's all zeros for all the other days, then the last day must be true. So we could drop Sunday, and so that would make 6 columns. So you basically get a column for each value. Again, I think you covered categorical data in stats class. I'm not really covering all of that, but this transformation of a column is all done in one line in scikit-learn. And you can see in pandas. So actually, so you see the PD dot here at the beginning that says, in the pandas library, use the get dummies function on the original data frame, because remember only my original has the categories in it. And I take the one column name that comes from my for loop. So the variable column name is set my for loop. So I'm doing this one column at a time. And then drop first means I'm dropping that extra one. So my category data frame is something where the columns are the binary columns created by the transformation, and the rows are our observations. So then what I do here, I do df. My data frame will be a concatenation. So Pandas concatenation can take two data frames. So in this example, my data frames have the same number of rows, the same observations, but different columns. And now I'm concatenating all the columns from numDF and catDF. And so DF is a new data frame that has all numerical columns and one categorical column transformed into its binary version. And the reason I put so many prints in here, I put a bunch of extra print statements. They're not really necessary, but what it does is shows you the number of rows in and columns in the data frame. So I want to show you that if you look at the first example down here, let me see, let me scroll this. So for example, the first column that showed up, the column name was gender. The transformation gives us one column. The numeric values give us 14 columns, and we add when we concatenate it, we have 15 columns. And so then we just do the same logit analysis we did. I moved my iterations up here to 2000. So when we're adding in a bunch of binary columns, you can really slow the calculation down. It tends to take a lot more time. And then, so for every one of these, I print the ROC. And so that's what you see in this. Let me scroll down a little to show you more of this output. And again, it's not really so much a class on stats, so you'd have to do some more analysis to see which of these you'd like. And I have not even gone into saying, well, what if we took multiple categorical columns and combine them? I didn't really go that far in this example. I've taken one categorical column. So if I add gender, I get the new data frame has 15 columns, and my ROC goes up a little bit, 611. Remember, my baseline is kind of this 610, right? This ROC of 610 is what I got with all numeric columns with one of them transformed. And so if I get anything above 610 here, it's a little bit of an improvement. And you can see, so we did this for gender. We did it for postcode area, right? So postcode area, there was, see this first 9 here, that means there's 9 columns, which means there were 10 postal codes in the data set. And so I added the 9 and the 14 and the 23, and that didn't really change our ROC here anyway, so postal code doesn't really help that much. Clinic ID, the second row, there's 15 different clinics involved. You can tell from that, things like that. So some of this I would have probably done more background research to know if I really want that categorical variable or not, but I just ran this for all of them. And the nice thing about Python is sometimes you'll just do numerical analysis on everything, loop through it. Some of it may not make sense, but again, with Python automating the system, it's kind of okay. So appointment time. This is something I would go back. So schedule date, right? There's 3. See the big number, right? Schedule date is probably not a good column to use as transform. I should probably do that a different way, or I probably wouldn't even use schedule date. I'd probably just eliminate it. But there's a lot of different schedule dates. So there's 364. There's 365 different scheduled dates. Therefore, 364 columns, 378 columns in the total data set, and it timed out. See this error message? The probability that, here we go. Failed to converge, stopped at number of iterations limit. So I had set the iterations to 2000. It needs a huge number of iterations because it's a huge number of columns. And in fact, schedule date is not a proper column for using for this. So I should just, it'd be better just to drop schedule date. It doesn't have any meaning. Appointment date, but appointment day a week. Now, appointment day a week, maybe that is useful. The ROC doesn't show much improvement, but that's theoretically useful. Again, day a week, the 7 days, drop one is 6, added to our numeric columns, 14 is 20. Reminder, did they get a reminder? Reminder, did they respond to a reminder? Was a reminder set out and did they answer that reminder? If they answered that reminder, that is somewhat predictive. It brought us up to our ROC of 0.63. So there's a little bit of value added in that. And we can see a reminder should be somewhat related to whether they show up or not. So, bunch of different techniques. This is teach you a bunch of things in Python more than stats, right? So you've got to figure out what statistic you want. You need to go back to your knowledge of statistics to what's appropriate for the machine learning scenario. But once you find that, all the techniques you need are going to be found in, some of it's in the base pandas, a little bit's in NumPy, a lot of it's in scikit-learn, and then other libraries here we've just touched on for displaying and the information. All right, well, thanks. And that is basically, think about this as this is sort of beginning to get you into machine learning, right? So statistics is the tool, is sort of the logical tool. Python is sort of the physical tool that makes it happen. Python with scikit-learn. And when we combine these, we're going to start in your future classes, you'll be combining these in new ways to create machine learning environments.